Okay, here's another device that has a spring in it. You can see that it has, we have two members here connected by a spring and cable connection there. I've got a roller there, a pin there. And if we read the problem, it says the spring has an initial length of 6 feet and the spring constant is 2 kips per foot. Okay, what do we get out of that comment? Well, we can get the force in the spring. So in other words, when you have a problem with a spring, generally you're going to be given some other information about it. It could be, the spring could be located in a scale, as we've seen before, or in this case, we've been given that the original length of the spring is 6 feet, and I can look at the geometry here, and I can use the Pythagorean theorem with this right triangle to get the new length of the spring. And then what do I know? I know that the difference between the new length and the original length gives me a delta, and then I've been given the spring constant K, and we all know that the force in the spring is K times delta. So I can compute, with this particular problem, I can compute the force in this spring. So that's what the problem is telling us. And then what we're trying to find is the tension in the cable at point C. So I want to know what that cable tension is, which means what? I have to, at one point or another, I have to make a cut through that cable to get the cable tension. So with that information, I am going to leave it up to you to do this particular problem. Okay, so pause the video here and do this problem. Okay, first of all, the only two-force member here is the spring. In other words, this is not a two-force member because it's attached at the ends here, and I have a force in the middle, another attachment in the middle. And similarly, I have the two ends attached there with another attachment in the middle. So the only two-force member is this one. It's a spring. We treat it like a truss member, as I said. We can get the original, we're given the original length of 6 feet. We can get the final length using the Pythagorean theorem, the square root of 8 squared plus 8 squared. And so the new length is 11.3 feet. So the final length minus the initial length is 5.3 feet. And since it's 2 kips per foot, that's our spring constant, 2 kips per foot times 5.3 feet gives us the force in that spring of 10.6 kips. I can take a free body diagram of this portion right there, and notice I'm making a cut through the cable. So that's going to give me the force in the cable. And so what do I have? At that pin there, I've got an AY and an AX. And at the spring, I know that it's tension of 10.6 kips from here. And then I have my cable force here, T. I take moments about A equals 0, and I have, minus T times 10 for that one. And I'm going to use the horizontal component for that, which is 10.6 cosine 45 degrees, which will go clockwise. So it's plus 10.6 cosine 45 degrees times 8. And that gives me a T of 6 kips. All right, here's another one, another device. This is a force of 40 pounds right there, is used to compress the material in blue. So let's look at what this does here. I'm pressing downward here. We're going to pivot about this point, and that means that downward is pushing in that direction perpendicular to the member, which is going to pivot about this point. It's going to go push inward there as we push it downward. In other words, as it goes, this point will move both downward and to the right. And this member here will rotate about point B. And the end result is that we can compress this material here. You can see there's a little piston there. And all the dimensions are given. I've got, angles given. I've got dimensions given. And I have the force of 40 pounds. So the problem here is to draw the final free body diagram of the piston and member BCD, which is that member right there. Look for two force members and do this problem. Okay, so pause the video here. Okay, so what we find is that member AB is a two-force member here. So this member is a two-force member. Now, that means what? That means that when I take a free body diagram of this member, I know that there's, I just have one force that acts along this member. So I'm gonna call it FAB, and I already know that this angle is 35 degrees, so that angle is 35 degrees. And I can get this, this distance h here by simply using the 35 degrees. I know that the tangent of 35 degrees is h over 9, because this is going to be half of 18, this distance here. So I can get h at 6.3 inches. So when I take the free body diagram of member BCD, I have the 40 pounds, of course. At point B, I've got FAB at the angle of 35 degrees. And then I have a CY and CX. All the dimensions that we need are given here. And I take moments about C, about point C. And so now what I can do, of course, is I'm taking moments about C. When I take moments about C, the easiest way to do that is to not break the 40 pounds into components, because I already know it's perpendicular to the distance that I know. So it's going to be minus 40 times the length 30. And I'm going to break this down into components because it is not perpendicular. So I break it into the FAB cosine 35 and FAB sine 35, and using the dimensions that I have here, we've done this enough times to take moments about this, so that's going to be times the 6.3, and that is going to be times the 9, and this one, of course, is clockwise. This one, of course, is also clockwise, so both of them are plus. And I can solve for FAB. I get 116.3 pounds. Then I can take the sum of the forces in the y direction equals 0, And so I've got the CY, everything in the Y direction is this. Now I have to break this into components. So I have the angle here, which is 55 degrees. So notice the angle with respect to the x-axis is going to be the 90 minus this angle. So I'm going to let you reason that out, but that's going to be 55 degrees. And so it's going to be, for the y direction, minus 40 sine 55. I put the 116.3 into that portion, and I get CY is minus 33.9 pounds. I take the sum of the forces in the x direction equals 0, so again I'm going to use the x direction, and then again I have to take the x component of that one, and I put those into my x equation, and I get, and again I put this 116.3 there, and I get Cx is negative 72.3 pounds. I then put those on my free body diagram with the correct directions, taking into account the negative signs here. Now that gives me the final free body diagram for this member. What happens to the piston? Well, again, we have adjacent free body diagram. So if it's 72.3 pounds there, going to the left on the piston, on the piston, it's got to be 72.3 to the right. So it goes to the left there, goes to the right there. And it goes down there. It means what? It goes up there. So I have, these are opposite. So what's on the piston, so now I can do the piston. I guess the way to do it, in a sense, is looks like this, is that I have the 72.3 pounds here. I have the 33.9 pounds there, and then I've sort of skipped a step, but the compacted material gives me, I'll call it an Fx, and then I have rollers for Fy. In other words, the piston the piston has to be in equilibrium also. So what we find is that the compacted material pushes back with 72.3 pounds, which means we compact the material with a force of 72.3 pounds. And so that answers our question. So we apply 40 pounds and we get a compressive force of 72.3 pounds. Okay, this is another one sort of similar, so I want you to do this one. And I'm just going to let you do this one again. Now notice I'm going to push downward here, and that's going to push that outward. This is fixed, so I can compress this material here. So pause the video here and do this problem. So what do we have? We've got the two force members here, and I'm pushing downward with the 50 pounds, so this takes us back to our truss problems pretty much. So I can take a free body diagram at point C. I have my FAC, FBC here, and we've done this many, many times. So I'm not going to belabor this, but I can, you take the sum of the forces in the x and y direction, and in the x direction, what do we learn? We learn that FAC is equal to FBC, and then we take the sum of the forces in the y direction. I'm going to let you do that. And we end up with FAC and FBC are negative 73.1 pounds each. So that when I look at my piston again, notice the piston, I've got rollers above and below here. So that's got to stabilize this piston. So I have, forces from above, forces from below. And when I look at this piston, again, what do I see? I've got my 73.1 sine 20 degrees going down, 73.1 cosine 20 degrees going to the right. And that means this piston has to be in equilibrium. So I have Bx and By, and I know that Bx has got to be the same as the 73.1 cosine 20 degrees. So that works out to be the 68.7 pounds. So I put 50 pounds here, I get 68.7 pounds there, so I get a little bit of an increase. Next problem. Okay, now we've got the same device basically, so notice I have the same configuration we just analyzed right here. But now I'm going to add to it, I'm going to add this handle here that's going to help us out a little bit. So now what I'm going to do is I'm going to press down here, and that member will pivot about point E, which will push point D downward, and then from there it's the same as what we had before, which the downward movement here is going to move that piston out, and we're going to again compress this material right here. So again, the problem is to find the compressive force acting on the blue material, but now it's due to this 40-pound load that we're putting on our handle. So I want you to use what we learned in the previous problem. And just to remind, what did we learn? We learned if we press 50 pounds here, I get 68.7. Well, if I put 100 pounds here, what are we going to end up with? Well, we're going to end up with 2 times 68.7 pounds. So the ratio stays the same. I think you can see that. So we can, you don't have to do the whole problem in a sense. Once you get that load there, you're going to just take the ratio to get that load there. Okay, so pause the video here and work this problem. Okay, so now I want to look at what's going on with this member, and I know that DC is a two-force member, so when I analyze, and then this ends up being a very simple problem now when we look at it, I can take moments about this point. I have my FDC, so this becomes extremely straightforward. I take moments about E, and I have, 40 times this total distance is 3 feet, and minus FDC times a half a foot. All that equals 0. I solve for FDC is 240 pounds. Well, okay. So now what do I have? My multiplier was 68.7 divided by 50, which is 1.374. So now I'm putting on 240 pounds. So I multiply 1.374 times 240, and I get 330 pounds compressive force at B. So our machine works a little bit better now, because now I'm putting on 40 pounds and I get 330 pounds. So by adding this extra feature to this compressor, we get even more force out of it. Okay, there's some geometry in these problems, and so all of it is high school geometry, but I know that you've forgotten some of it, and I need to refresh your memory, so I'm sort of going to make you do some geometry here to solve this particular problem. So first, we just want to focus on the geometry, and so let's start there. We'll take it step by step. This somewhat simple problem is complicated by the geometry, so I want you to focus on it. So here's the problem. The ball weighs 300 pounds. So I've got this ball here. It weighs 300 pounds. And we have rollers at points A and C. However, the rollers are contacting planes in both the X and Y directions. So these are not rollers that only contact in planes that are, X direction planes. They contact both the X and Y, so they're like that. So they're not really rollers in a sense, they're more like pins. And so I'm pointing this out because you may see a problem like this on the Fundamentals of Engineering exam or something like that. But so you need to know how to handle this particular type of connection. And so we have both X and Y forces at A and C, points A and C. So down here we have both X and Y forces. What I want you to do is to draw the overall free body diagram and calculate A, Y, and C, Y. Okay, so before I do the geometry, we're first going to look at the reactions here at these points. Now, notice I only say calculate A, Y, and C, Y. I don't say calculate AX and CX. So start there. Draw the overall free body diagram. So when I say the overall free body diagram, I mean this. And calculate just AY and CY. You don't have to calculate AX and CX. Okay, so pause the video here and do that. Okay, so it's pretty straightforward. I have a free body diagram. I got the 300 pounds acting down the middle. I've got the AY, the CY, the AX, and the CX. So I have to show them all, but now when I calculate them out, well, what can I do? If I take moments about C, for instance, what happens? Well, AX and CX go through that point, CY goes through that point, and so I only have one unknown, and that's AY. So I can calculate AY by taking moments about C. So, and I'll just let you read it. It ends up to be 150 pounds, which makes sense because everything's symmetric here, right? So, and then I can do the same thing. I can take moments about A, and again, all these things go through it, and I have CY, and of course CY ends up to be 150 pounds also. So notice we cannot solve for AX and CX using this free body diagram. So because I've got 4 unknowns here, and I only have 3 equations to work with, so I cannot solve for AX and CX with just this free body diagram. So the techniques we're going to do next, we're going to be able to solve this, but there's some issues. Okay, so this is where I want you to use your knowledge of geometry to calculate the angles alpha, beta, theta, and gamma, and then calculate the distance d. So this is the geometry strictly problem, part of the problem that I want you to do. So here, where are the angles? So I've got alpha here, beta also here, theta here, and gamma right there. So we've got all those angles. It's not hard. This is high school geometry, but I want you to work through these because these are all part of the problem, and then I want you to calculate this distance d here. So now notice I have the ball, and the ball, of course, contacts these surfaces at a tangent. So that's a right angle. And that's a right angle. Now, just to be aware of what's, suppose I have my a different geometry in a sense to this, so let's just take it in an extreme. Let's say I have my geometry looks like this, and then I put the ball down. So then I have, well, and let's just actually take a big ball, and I'm going to put that ball here. Looks like that. Now what do I see? When the geometry is going to be, I have my, it's different. In other words, you can see that the angles are all different, and so you cannot make the assumption, for instance, that theta is 90 degrees or anything like that. My theta would be, now my theta is this. So the dimensions and everything for each case, depending on the size of the ball, depending on the configuration of the x, the x being this part here, the configuration of the x and the size of the ball will all change the angles. So be aware of that, and I want you to I want you to solve this problem for these dimensions. Okay, so pause the video here and solve the angles alpha, beta, theta, gamma, and the distance d. Okay, how do you get these? Well, let's start at the bottom here. And there may be simpler ways to do this, and you may know geometry even better than I do, so you may even see a faster way to do this than I'm showing you here, but this is one way to do this. You can do it any way that you want to get these angles, but if I look at alpha is the arctangent of 2 over 1.5, well, what triangle am I using here? I'm using this triangle right here. So I know that 2, and then this distance is going to be 1.5. So that's easy to get alpha. Now once I have alpha, what do I know? Well, then beta, or half of beta is right there in that triangle. So I know that one way to look at it is that beta over 2 is going to be equal to 90 minus alpha, and so beta is going to be equal to 2 times 90 minus alpha, and so that beta ends up to be 73.7 degrees. So I now have alpha and beta. How do I get theta? Well, now what? Now I've got this quadrilateral here, and I know with that quadrilateral that the angles all add up to 360 degrees, and I know that this angle is 90 and that angle is 90, so 360 degrees minus 90 minus beta, that gives me theta. So theta is 106.3 degrees. And that means that theta over 2 is 53.15. So now I'm going to look at, for instance, this triangle here, and that has, if I look at that little triangle there, and then like I say, there are other ways to do this, but what do I know? I know that theta over 2 plus gamma is equal to 90 degrees, and then theta over 2 is 53.15. So I get gamma is equal to 36.85 degrees. And okay, so I've got all that. Now now my goal is to get this D, and so I've got all my angles and things like that that I want. I now can use this triangle, which is this triangle down here, to get the distance D, and so I have these angles, which I've got the beta over 2, which is 36.85 for this angle. I've got the theta over 2 for this angle, and I've got the right angle here. I know that that's 1.25, so I can get the distance D, looking at this, as the tangent of 36.85 is 1.25 over D, and I get that D is equal to 1.67 feet. So those are the angles. Okay, so now I'm starting to get some information about this problem that seems to be quite simple, but there's some issues here with both the reactions and these angles and distances. So now we're getting to this problem, and it says it's a frictionless ball, and now I want to find the forces acting on the ball. So with all of that in mind, I now have all of my angles here that I've learned, and here's what it looks like. I've got my D, and I've got this angle here, and so now what I want you to do is to find the forces acting on the ball. So go ahead and do this problem. So pause the video here and find the forces acting on the ball, given everything that we've figured out at this point. Okay, so it's pretty straightforward. I just take this free body diagram of the ball. It's a frictionless ball, so that means that, the forces at the tangents go straight toward the center of the ball. So, and I've got the weight of the ball is 300 pounds. So I now have FE and FD, and I simply take the sum of the forces in the x direction. I've got all the angles, and I find that FE and FD are equal. Then I take the sum of the forces in the y direction, and now I just use the sine of the angle to get the vertical component minus the 300, and I get that FE and FD equal 250 pounds. And then the last part of this is using the information we've calculated, draw a free body diagram for member ABD. So that's this member here. And what we did just calculate is this. and so I'm sort of showing you the free body diagram. This is what we've learned so far. One, we've learned this is 250 pounds. I know the angle here. I know that the Y reaction at point A is 150 pounds. And so I'm left with AX, BX, BY. And so, in a sense, I've drawn this free body diagram for you. Use this free body diagram and find the unknown forces. Okay, so pause the video here and do that. Okay, pretty straightforward. Once we have this part of it, I can take moments about B and I now have, all the dimensions that I need. So again, I now have the distance D. So that's this distance. There are other ways we could have done this, but I now know this distance is 1.67, so it's going to be 250 times 1.67 for when I take moments about that point for that 250-pound load. And then I have the 150 is what? It's going to be, I know that's 1.5 there. So 150 times 1.5 for that load. And then I have AX, it's counterclockwise, so it's negative, and the distance is 2 feet. I get AX is 321.25. And then I can take the sum of the forces, so that gives me AX. Now what about BX and BY? Of course, we can take the sum of the forces in the x direction equals 0. And that is, so I have my AX and I've got BX, but then I have to do my 250. Well, I have to use that angle that we had to work hard to get. And so that's going to give me 250 cosine 36.85. And I solve for BX, it's negative 521.3. I take the sum of the forces in the y direction equals 0. And again, I have to use that angle of 36.85. And I use the sign because I'm taking the sum of the forces in the y direction. And I get, interestingly, by equals 0. So the end result is that my final free body diagram for this member is this right here. So in summary, it took us a lot of work to get here. Let's, in a sense, let's review. We could not get initially we could not get all the reactions here by taking a free body diagram of the whole thing. So, so to be able to solve this problem, we had to look at the free body diagrams of the individual members. And we don't have to do this one because everything's symmetric, and this one is simply this one in reverse. So we only really needed to do one of those. Now, what we found, though, was that for this very simple problem, we had to work hard to get these angles and distances. So when we have this ball that we're put in. So what I'm pointing out here is that when you can have some complex geometry, even though it appears to be simple when we start throwing in balls and things. So that is lesson for this seemingly simple problem. So, okay, we're done with frames and machines.